Hi, and welcome to the Huxter Group. We're an interdisciplinary group of researchers from chemistry, physics, and optical sciences using ultra-fast laser pulses to study redox active systems, catalysis, and quantum materials. I'd like to introduce you to some of the great graduate students in the group and let them tell you a little bit about some of the work that they've been doing in the lab.
Hi everyone, welcome to Huxter Lab. I'm Anshu Kumar and I'm a graduate student working in Huxter Group. Today I'm going to show you a small tour of our lab. So let's start first with, this is our main laser system, which gives us 800 nanometer wavelength light, as I will try to show you here. As you can see in this card, very bright, right? Okay, so we take that 800 and then we pass it through this OPA, and voila, we have a 600 nanometer wavelength coming out. So we can use OPA to change the wavelength to as our desire. Then once we have our light passing through, we send it through a prism compression line. You can see these nice prisms. We have a pair of prisms, and the idea is that we pass it through the prism compression line so that we can compress the pulse and remove the chirp the pulse might have. And then after that, we take our output, as you can see here, and send it to our main 2D setup, and that's where all the magic happens. Right here is the 2D setup, and that's where we are able to have a resolution in femtoseconds to examine the dynamics we might be interested in.
Hi, my name is Benjamin Thompson, and I'm a student in the Optical Sciences department working towards my PhD in the Huxter Lab, seen here. And what I'm working on currently is developing a white light laser source for our two-dimensional electronic spectroscopy experiments, which we'll use to investigate the energy correlations and dynamics in our samples. This is the white light that we generate. It's pretty bright and it has a lot of wavelengths in it. Dimmed down in a back reflection right there off of one of our square optics. But this actually comes from the original fundamental 800 nanometer wavelengths that you can see pretty bright here, right like that.
Hi, my name is Alicia Swain and I am a physical chemistry grad student in the Huxter Lab. I'd like to show you something that we work on here in our group. Okay, I'm in the lab and I'm going to show you the fluorescence upconversion and TCSPC setup in our lab. We have our high sapphire laser that can generate 800 nanometer pulses that we send into our optics to generate 400 nanometer pulses, and we can use that light to excite fluorescence and measure time-resolved dynamics with TCSPC and fluorescence upconversion. Okay, and for the first example, I'm going to show you a coumarin laser dye in our 400 nanometer beam. And you can see that we have some pretty bright greenish fluorescence. And then if I take this out, I also have DCN dye, which is one of my favorites, and it's a pretty orange. And there we basically take our fluorescence and detect in a PMT in this box, and that's how we can get some of our dynamics.
As you can see, we build our own instruments to map energy dynamics across the entire visible range. We've got a lot of really exciting research on the go right now, and we're looking for some great graduate students to join us. Thanks for stopping by, and we hope to see you soon.